why not?
This is surprisingly crowded.
Yeah, we were originally told that there might be like 1, 2, 3 people now. Of course, a little bit more. We'll see.
Okay. Hey, this is Sean Parker, and I'm Paul Schröder, and we're here and tell you something about testing software on emulated hardware in containers, in the cloud, and I hope you all like that.
We think it's quite fancy.
Yeah. We tell you something about the project, why we're doing this. It's high-level architecture. It's high-level architecture. The test pyramid, where our stuff is located in the test pyramid, about the target devices and the challenges related to them, a little demo, and in the end Q&A and recap if there's still time left for. So we're working for an international train company, and it's not about cargo, it's about traveler information, like the thing below. And you might all have experienced the delays, and so like 5 minutes delay on the display, and 5 minutes later it's 10 minutes delay, and 10 minutes later it's 15 minutes delay. And the reason for that is the federated decentralized system of servers serving all these displays. And if a train did not arrive in the visible area of this server, the operator doesn't know when it will arrive. And so he's just starting to type 5 minutes, and 5 minutes later, if the train's still not arrived, he's increasing that. So the goal of our project is to centralize that. We have a partner project in another city which is doing this consolidation of information. If you have conflicting sources and conflicting information, which source do we trust more? And this is a tough problem on its own, but it's thankfully not ours. And we're more focused on devices itself, the management of them, and the rendering for the different display types. Yeah, and this is where I hand over to Sean.
Cool. Yeah, so I mean, Paul already mentioned that like the old system was a federated system where depending on where the information display is, or perhaps where the train is, the information might not propagate properly like to the end station. If you have a train starting, I mean, I don't know, it's like 8 hours early, like in a totally different part of the country, the information displays are currently with our client perhaps not timely updated because yeah, the flow of information is just not giving that information. So this now is basically a simplified abstract version of what we're doing. So basically Paul just mentioned the system that is basically at our other project consolidating the data. So and they're planning basically delays and updating the information continuously. So in the background, we have something like a RabbitMQ broker where you can basically subscribe to a certain train track and so forth, and then you can basically get the information and you continuously update it. Sounds easy, is actually quite complex. And I mean, it's improving from year to year. But what we are then doing is, I mean, the other project is basically the external domain up there. So there's single source of truth block of travel information. That's basically where all the information goes in. So train delays, when the train started, when the train arrived, scheduling, and all that kind of stuff. And it's also basically interfacing in the background with information systems from other countries or other operators. So that's where all the information goes in. And our project is basically interfacing with that. And you might see at train tracks different devices, basically voice devices. So basically if a voice announcement comes, that's from one of those devices. If you have those displays, LCD of TFT, the old ones and the new ones, that's one of those devices. And they might still have a variety of sensors. So you could think of our system a little bit like Netflix for travel information. So we have a big microservice architecture in the background, and depending on demand, I mean, you can imagine during the night, there is not that much going on. I mean, there are cargo trains, there are night trains, but really rather during the rush hour, we have like most of the information going through our system. So it's growing.
It's really pretty much like a sine wave. over the day and falling down in the night.
Yeah, indeed. So, and what we are focusing on, I mean, this backend block, without getting too much in the nitty-gritty parts, is already complex enough. So that's the Netflix bit. And then still we have quite a lot of different devices we have to interface with. So those devices are quite often, well, paid by public money, so you can't just replace them. So you have to basically retrofit them with a new operating system. That's what we're doing, because I mean, there was no clean standard basically in the past. So for instance, we had a lot of different device types with different interfaces, and that of course doesn't make it that easy to integrate with them. So we're building a new operating system, and hopefully it will work quite well in the future. So, and that's what this talk is about in its core. So this little OS box, we're building the operating system based on Buildroot. Who knows Buildroot? Quite a few, good, cool. So it's basically a toolbox, really in an abstract way. It's something you can use in order to build a Linux operating system and customize it to your needs. Yeah, and we're doing that, but that's of course quite difficult because testing hardware or testing software for hardware with different configurations, it gets complex quite quickly due to combinatorics. Cool. Yeah, so who of you has seen a test pyramid so far? So probably you have experience in the enterprise domain or somewhere else, or you have made some nice PowerPoint slides about that to convince your manager that it might be reasonable to write a few tests. Yes, that's a good idea. So integration tests and unit tests, that usually happens with software, but at some point you have to integrate it with the real world, and that's usually where things blow up, and you actually want to find bugs and problems as early as possible, because I mean, in the beginning, if you have a unit test, right, it's like you find a bug, it's just like you fix something and recompile and it's done and it's good and you're happy. But if the client finds a bug, it's like you're getting called, ops is unhappy, you have to roll out everything, you might have to wait quite a long time in order to get your fix out, and it's just not making me as a developer happy, because basically my development flow is broken. But yeah. Long story short, you just want to find bugs as early as possible, and that's what we're doing with those operating systems, which we put in containers in order to run them in the cloud, because then we can do that at scale, more automated in the CI, instead of flashing it or automatically flashing it to a limited set of devices and testing it manually, because there we are basically limited to what we have hardware-wise, and you have to be there physically. Cool.
The stuff we want to present you fits in this column of in this row of the test pyramid, and the target devices are pretty. There's a huge number of them. I guess 6,000 at least. A lot of different types. Most of them are. The old ones, like the LCDs over there, are PC104s, the form factor, but they vary in CPU, in RAM size, in CPU types, in the interfaces. You have these LCDs and the TFTs, which are like better TVs, but they are powerful quad cores with gigabytes of RAM, and the outputs are different. We have different boot mechanisms, like some devices only support UEFI, but the older ones only support MBR. And our goal is to have like one image that runs on every single device. This is not possible. We have a variety, but still we want to have it reduced and not extended to have it still maintainable and testable. There's different, this is just the devices itself. There's different external peripherals, like it's called Zughaltsensoren, train stop sensors, let's call it like this. The displays are sometimes controlled via serial protocols. UART or RS485. Some some sensors are connected via I2C. Sometimes there's special translational hardware which presents itself to the system as an graphics card, and the whole thing gets translated into pixels down to the LCDs. So proprietary old legacy stuff, no source, and there's sometimes a lot of reverse engineering involved. And because some of the suppliers of these devices are not are
They're off the
bankrupt.
market, basically. Yeah, they're bankrupt, or they've been bought by a different company, and they're not, to say, willing on cooperating, like basically helping us. I mean, it's like, it's all closed source software, so why should we help you? Because then in the future you might do everything yourself. Maybe.
Sometimes they even don't have the source themselves anymore. So sometimes they go down in the basement and have a look in their in some, don't know, file folders and like real paper and stuff. Anyway.
It's quite interesting. Sometimes you basically log on to those old machines and you have a look at the history and people jumping from one machine to another in order to fix a bug because they don't know. Yeah. But so that's something we really want to fix, because that's something you can, well, you probably know yourself, that's something that is not maintainable. So we really want to push a standardized interfaces, so it will be maintainable and will make us as, I'm a DevOps guy and he's more a developer guy, but that will make me personally really happy if that works.
Yeah, the standard workflow of the suppliers was have one Debian image, put their software stack on it, put it in the device, fiddle around till it works, and then never touch it again. And what we're trying to do is like automated updates in the field, and on 6,000 devices with thin network lines with sometimes only 10 KB bandwidth, you really don't want to push that often an image through it, especially if it's like 200, 300 megabytes. So we would like to test the stuff before we roll it out and make sure that it's working like we want it to. But the problem now arises that we have like a huge hardware variety, and how can we simulate that hardware in combination with the software we want to run it on? And we're trying to use QEMU. The QEMU is pretty awesome because you can really fine detail specify how the hardware should behave. You can select different CPUs. You can connect different serial devices in different options, like is it connected via an ISA bus or a USB, and you can change the details of the DMI table, which is like a specific part of memory on the hardware motherboard itself. We heavily rely on that to identify the different devices. So in order that we know what services we have to start and which not. So on a TFT, you need, we use there an electron to display stuff, and on an LCD, we use like custom written controller service, which is communicating with the LCD displays. So yeah, we choose QEMU and it's open source. So this is the container, how it looks like. It's not what we're using on the project, but it basically reflects the state of the composition. You have the outer container, it's an Alpine, where is QEMU installed. You have an inner QEMU running, which gets the disk image via a volume mount. And some ports are exposed, for example, the SSH, to remotely control it. In the future, we would like to get rid of that and do everything by AMQP commands, but this is still far future.
Does everybody know what AMQP is? Basically, the protocol used by RabbitMQ, which is our middleware, middleware basically, message broker.
And So the interesting stuff for QEMU is the dev TTYS0, which gets exposed on a socket 9000 and can interact with external hardware, in this case with a mocked hardware. And the control port of the mocked hardware is also exposed. We have a no VNC, which lets us see how the boot process is, but really the yellow stuff is only optional. It's not really necessary for testing the image itself.
Yeah. So it's quite nice. So Nova, you know VNC? It's basically HTML VNC applet basically. So you can browse to port 6080 and basically see what is going on that machine, and you don't need one of those applications installed. So it's tightly coupled in there. So what we have been doing at our project, we first did that actually with graphical applications with a no VNC in a container. So we were running up to 600 of those devices, and you could just click a link with a unique identifier of the simulated device, and you could see what's going on one of those devices. So that's really helpful if you want to stress test your system with real devices.
Especially the back end, not the devices itself, to generate load on the back end.
Yeah. Cool.
Okay. What you're going to see is something like this setup. It's not much different, but the mocked, you see like the mocking part is deleted, and the TTYS0 port is just like exposed by the Docker container, so we can interact directly. So we kind of doing the manual mocking.
Yeah, so what we're going to show you basically how that thing works. We're going to do that unfortunately locally because we can't interface with our client's CI/CD system at this point because we didn't get approval, but that's fine. I mean, we didn't get an answer so far. So that's why we're showing you it basically, and then we're telling you how we are doing that currently in the CI/CD context of our project and how we're deploying that.
Okay. Demo time. I guess ich glaube, wenn ich es spiegel, wäre es besser. Okay. Windows P. Ah! Mirror, yeah. Yeah, give me a second. Ah. Okay. Perfect. So there's the Docker file, which builds like the container you've seen so far. There's this QEMU disk image. I was trying something that's not so interesting. We have a make file, which should make it easy to do stuff right now, but we can make run Quokka. So we're still attached to the container, which boots up right now. So we have a little delay between the QEMU start and the no VNC start, because if you start them right after each other, sometimes no VNC says it can't connect to the VNC port of QEMU. So details not so important. The next interesting thing is
Touch on the running container.
Yeah. We can have a look at the booting container. Which looks like this. So this is what you would see if you would start QEMU manually. And you could interact, but I guess here it's disabled. We can now connect to the to the running session inside. And the service running inside runs in an tmux, so I can attach to the output again. But on boot it starts as root, so we have to sudo tmux. We can ls first. We see a session running. We can attach to the session with this name. So there we see that the HTTP server started and the sensor handler started on the dev-tty as 0 with the given baud rate. So now we have a look at the service we want to test, which is on local port 8000, which looks like this. So far it hasn't received anything. I'll make this a little smaller that you see. Okay, and then we can send some data. We're not waiting for a response. Q0. Connect to localhost and the exposed port, and let's try this. So you see the sensor received some raw bytes, decoded them, stripped them, parsed them to int, and if we so thanks. If we plug something in which is like non-parsable as an int, we see that an error happened, and a test scenario would be put garbage in and see if it's got parsed by the program itself. Wait. So let's see, it didn't change.
Yeah, so what we're, for instance, doing with sensor data perhaps is all our devices basically have a exporter endpoint basically. So Prometheus is basically scraping metrics from that system, and well, it then basically when Prometheus digests all those metrics, and we can do later on something with that. Quite interesting to see in the morning where the sun is going up or how bright it is or whatever. But it's also for diagnostics quite interesting.
So I just go back a little. Too comfortable. Yes. So we pushed some data in here. It got processed by the custom service and got exposed on the 888 port again. So this is like a round trip through the software to test. Yeah. So since it's Dockerized, you can put it on Kubernetes and put it in the CI and run tests on it, do it automatically. Yeah.
Yeah. So what we're doing, we have for our project still helm charts, which is the configuration layer. You basically tie around one of those Docker containers, and then you can basically mount the newest build or OS image you want to put in there. Then basically run it, and you also through Kubernetes can tag it, put all the metadata into it, and run it at scale. That's actually quite helpful for us at least, because now we can basically show the client what we're doing and what kind of different configurations. It's retestable, which is usually not the case with hardware. Probably a few of you have tried replicating things with hardware. It just takes a lot of time. Okay.
As you see, it's not silver bullet because like this special hardware is really hard to mock. Special graphic cards you can't really mock in QEMU, and this is not feasible. But the standard cases are doable, and it's not possible to have a sample of every hardware configuration in the lab. First, we would need like a warehouse to store them all. On the other hand, you would have to plug in like the images or like deploy them via updates, but still. And you're not really controlling the input on the test. You're just testing that it's doing something, but you don't know if it's doing the right thing, for example. Right. If you can't control the temperature sensor. Right. And so this approach makes it kind of possible to get rid of all these problems, and not all of them for sure, but get rid of some of these problems and make the workflow a little more streamlined. Okay.
Cool. That was it basically. So we're open for questions if you like.
I guess we have plenty time for questions. Oh, go for it.
Do we have a microphone?
No, we don't have microphone.
I have to repeat the question, so it's...
Okay.
So you mentioned that you guys have a lot of powerful legacy machines, so these are quad-core machines.
No.
This,
yeah, go on.
this to me sounds like a botnet in the making. Did you guys ever run into any problems with that? Did you know of any of these machines that were hacked in the past? Please repeat the question.
The question was if these old legacy systems were hacked, if that's correct. Yeah, yes.
Second question.
Okay.
Why is it even possible to install custom OSs on these machines? Most of these legacy systems typically don't allow you to do a lot of stuff with them. So do you guys have like another part of hardware already installed in the stations that you can do anything with?
We actually have a lot of those devices shipped to our office, so we have a quite big laboratory where we can test quite a certain range of models, but our office is quite stuffed with it, so I mean that's our bottleneck. We can test a few of those devices live at the stations, but from a security standpoint of view, we try to limit the access to the network. For once, because of past happenings, and security is also a reason why we're doing all of this. So we can basically close down the operating systems and.
Yeah. The workflow, how the suppliers deployed a new image was like a guy was going there, opening the device, putting a CF card in there with the new image and fiddling around. And so, if that was a question.
When you guys actually develop these mocks for like hardware, you basically do it by experimenting with the live hardware in your lab, right? And then just coding the behavior that you see. So you're actually just reverse engineering.
Yes, the mocks are getting developed by reverse engineering. Sometimes there's a spec, but usually it's wide as a door, and every vendor made its own solution to that. Okay. You first.
Have you considered Linux kit as an option to build the operating system?
There was a, if we have considered Linux kit, I guess so. The decisions were made before I came, but we have good architects, and I guess they did so. But I can't tell you why the picked build route. I think because you can choose pretty specific what driver, what core utility you want to have in there, and if you really need it, and I guess that was the reason for it.
So back in the time, build route basically seemed like a good option. So when we started, well, when the project was started, was not quite sure what variety of hardware is out there. So I mean, of course you test against what you know, or you basically build your architecture against what you might expect. And at that time we had a certain amount of knowledge, and build route was basically fitting for that. I mean, it's a long-running project, so we haven't started like yesterday. So yeah, it's,
Linux kit is quite old also. So
yeah, cool.
I was interested about the options. Why?
I'll check it out. Yeah.
Yeah, if you are interested, just drop us a note and
Yeah, we have the code basically in a public repository, so we probably gonna publish that. Is that possible? Cool. Yeah. So you can have a look at it.
okay.
So you talked about using Helm to deploy these, and you showed us the developer experience. That
Yeah.
was really nice. Do you also have some CI looking into this? So as you push things up, are things tested, or is it very much aimed at the developer?
It's complete. It's like our project is completely built in the CI. So we have a GitLab CI system, and as soon as you push, basically, it's through the hook. Basically, it then builds all the code and deploys it automatically. If that was it. So it's again.
Yeah. So you were talking about exposing those ports,
Mm.
and then does your GitLab runner, the thing that runs in your GitLab runner, then point at those ports, or is the GitLab, does that thing sit in such a run?
So at the moment, it actually just deploys it. So the life cycle of the deployment is there independent from the, let's say runtime of the CI, or deployment basically. We haven't integrated that at this one so far because the requirement was we just want to see what is running on there and if it's crashing. And that's something you can see over time quite well in Kubernetes through logs, metrics, and so forth.
Another thing, like compiling build root is like a huge deal. It takes really long, even in the CI, even with heavy machines. So it's not like we reduced it down to 1.5 hours, I guess, like with the whole tool chain, but still you want to have it automized. You can't wait, click a button and wait for it to compile. There.
Are you able to boot the same images that are for your target hardware in QEMU, or are they like two separate projects?
If we build separate images for the target hardware and the QEMU, no, we don't want to do that. So we want to test the real image which goes into the fields, not a specific image for QEMU. We are having some kind of a variety for some in-house monitoring, but this is not going ever in the field. Down there.
Yeah, you said you're using GitLab CI for integration, and you're building build root, and you said you shrink the time. Are you using any caching mechanism between builds, or are you building from scratch?
If we're using caching for the build root part,
Caching between
Stages.
runs
Yeah.
or
Yeah.
stages.
yes, we're caching the tool chain. So usually build root builds the tool chain as well, especially if it has a blank system. And but what things would really speed up is the CC cache, but we didn't get it working till now. But this would be a really boost. Like, I guess we could make it in half an hour if we do so. Someone else? I guess then we're spot on.
Perfect. Thank you very much for your time.